Our next speaker, Thomas Sermpinis, is the technical director at Auxilium Pentest Labs and an independent security researcher, specializing in automotive, industrial control, embedded devices, and cryptography. In his talk, The Matrix Unloaded, Escaping the JTAG Reality, Thomas will explore how hardware vulnerabilities related to interfaces like JTAG pose security risk to the modern vehicles. Please join me in welcoming Thomas to the stage.
Hello, everyone. I'm honored to be here. Thank you to the Off by One conference. Thank you to all of you, to the speakers that made my job here really difficult to keep myself up and be up to the spec. I'm really honored to have you all here. And yeah, basically, I'm expecting to get some laughs out of you due to the political, social, and technological situation that we are living in. And yeah, so follow me and welcome to my talk, The Matrix Unloaded, Escaping the JTAG Reality, where we will talk about some disturbing cases of hardware hacking deriving mainly from the industry. I'm in a love and hate relationship with the automotive industry. I'm Thomas Sermpinis, also known as Grow Tom, and to know about me, you can, of course, go to my website, but TLDR version is that I'm the CTO of Auxilium Pentest Labs, leading an amazing team of car and embedded hackers, full of passion for the same reason that we are all here today. I'm also leading several other endeavors in the security industry, but during the night, I'm focusing on my independent research when I want to hack anything and everything that comes to my hands. Of course, like most of us in this industry, I'm a major InfoSec complainer, and I love criticizing constructively every company that makes stupid mistakes in my industry, resulting not only in millions of dollars in losses, but also potential lives at stake. But for you to get a better hang of it, we have to start. And I should start by saying that I'm 10 years in this industry, and almost nothing has changed significantly to make me stop complaining, criticizing, and trying every day to make the world a safer place. Now, to get on track with this specific talk and to give you a taste of what is coming and what we will talk about, we will mainly start by analyzing the state of cybersecurity in the industry I'm most experienced in, the automotive industry. And of course, this industry takes a lot of its characteristics from the embedded world, with similar architectures and pitfalls, but in a completely different range of products with not only privacy at stake, but safety as well. For this reason, we will also talk about all the stupid things that this industry is still doing. And in my talk, we will mainly focus on the hardware side of the things, with a bit of forensics in the mix, as some manufacturers really try hard to find strong excuses to why they don't remove debug access from safety-critical hardware components. Let's start by analyzing the current state of affairs, or the current state of my life in cybersecurity. And here you can see one of the best examples of what I'm trying to talk about. Usually I start my talks by showing a really futuristic vehicle, like the BMW Series 7, with all the bells and whistles that come with modern vehicles and all the interconnectivity that comes with them. But for once, let's dig a bit deeper and go from the holistic to the microscopic side of the hardware. Like with many sciences, there are several ways to perceive and analyze things, and here it's no different. Usually during my work, I try to analyze those things holistically, take the vehicle as a whole and try to understand how it works, how it functions, and as a result, analyze what threats would be applicable to the target architecture. Here, though, let's take it from the opposite side, and you can see that we have a really nice ARM processor from Giga Devices, which, to tell you the truth, it was the first time I heard about at the point the picture was taken. On top of it, we can immediately distinguish something familiar for many, an SWD port. Not to spoil it from here, but let's say I'm always happy when I know that my eyes don't have to get like this while micro-soldering JTAG headers like this. And believe me, throughout the years, these haven't changed much. From the early days of hardware hacking, trying to free your iPhone from its chains, and most recently, bypassing read protections with simple fault injection attacks in exotic automotive architectures, the starting point was the same, an exposed interface leading to the debug traces of the target chip, which exact traces were not removed from the target board for questionable at best reasons. And of course, other hardware attacks that don't require millions of dollars worth of equipment are also applicable here. A really good example, the really amazing talk from Sergey yesterday on the Xiaomi watch. And zooming out to the most not so futuristic car of the present, a JTAG interface might seem like an unreasonable concern. But what happens when this JTAG is the only barrier between a malicious group and the manufacturer's intellectual property? What happens when hostile nations start analyzing and using vulnerabilities that invade not only your privacy, but your safety as well? And not by dynamic and time-consuming blind methods, but by supplying everything to their plate. What happens when inexperienced and naive users take the devices in their hands and tune them with devastating results? Who takes the blame and whose head is on the line? That's the current state of cybersecurity in my industry. And despite the best efforts from researchers and people like us around the world, more and more functionality is packed in our computer on wheels, with security being heavily neglected and overlooked. So let's start and let's go through some real-world examples of debatable vulnerabilities from the past that still apply in today's world and sparked a lot of discussion throughout my career. Before we dive into the problem and the widespread hardware vulnerabilities I've encountered, we need to build a basic understanding of the attack surface and how it can be exploited not only by attackers, but also by hobbyists and smart home enthusiasts. What we will discuss is rooted in years of accumulated vulnerabilities, with the main goal being the liberation of our home devices and the second life we give them after being subjected to the planned obsolescence imposed by big corporations. Let's start our journey from late last year, after my trip to DEF CON, when me and my team was trying to think about the next steps in our research. Of course, something that many of us want to do as a direct outcome of our research endeavors is to get a direct outcome of our research, compete and challenge ourselves with other people following the same passion and maybe get something out of it on the way there. So with the announcement of Pwn2Own Automotive 2025, we decided to purchase one of the targets. For those who don't know, like it was discussed also previously, Pwn2Own is a live competition where targets are given to researchers around the world prior to this competition, and the researchers have some months to uncover zero-day vulnerabilities, which then have to prove live at the location of each competition. Due to the rising significance and relevance of the automotive industry, ZDI decided to create a dedicated Pwn2Own targeting only automotive components. So we went through the big list of targets and decided to focus on the category of chargers, mainly due to our experience researching charging protocols, but also due to the limited research that has been performed in the past on those devices. We purchased our target, and after more than one painful month of waiting for it to ship from Amazon US, the Wolfbox EV charger was in our hands, and we started the research. Now, to get the hang of what we are talking about, maybe I need to do a really quick introduction into hardware debugging interface. And basically, they mainly allow direct, low-level access to a device's processor and memory, intended for development, testing, and debugging. And there are several ones, but the most common ones, and the ones that you've probably heard of in the past, are the JTAG interface, which is old but still really common, especially in the automotive industry, SWD, which is an ARM-specific, lightweight JTAG alternative, and it's very popular in modern MCUs, as we will see later on in this talk, and UART, which is just a serial console that is commonly misconfigured and a really easy entry point for attackers, for which we will also see some examples today, and how it helped us extract some sensitive firmware. And finally, SPI, which is handling the internal buses mainly for firmware and configuration access. While JTAG and SWD come in several different shapes and forms, with or without headers, with all the pins needed or not, UART is usually a more simple and aged protocol that we will see in the wild. Now that we've got this basic introduction on the available interfaces that can be found in hardware for these debugging purposes, we can also imagine how a hardware analysis of the target would look like. When we first tried to pry open the device, we were introduced with this, and the most interesting part in this case, and in many cases apparently, are the descriptive markings around the board. Some would expect that in production hardware, markings that spoil the placing of sensitive components would be stripped and covered. But in most cases, that is not true. Not only we can easily see where are the power and ground pins and the required voltage needed in order to bring the device up, but the headers are placed all around the board, making our job of bringing the device up and working with it a walk in the park, with zero soldering needed or reverse engineering skills. Of course, the first thing we see, and our main point of interest, is the main MCU. After a little research, we find the exact chip model and its datasheet. This gives us way more information about the device, but something that is even more interesting is the header we saw on the start of the talk, which in combination with the datasheet and the fact that the MCU is an ARM-based chip, it tells us that it's an SWD interface. At this point, of course, I wasn't too excited, as probabilistically speaking, I was expecting this header to be locked. So I fired up my trusted J-Link debugger and connected it to the exposed SWD interface, started the client application, and tried to connect to the target charger, with the expectation that I will get some password prompt or the middle finger altogether, but I guess not today. This off-the-shelf production device came with a completely unlocked debugging interface, which just gave me complete access to the runtime and memory of the unit immediately. And after some minimal research over the chip's datasheet, we can easily find the memory map and the specific memory addresses that are of interest to us. From bootloader to the main flash, we were able to just read about anything that our heart desires, and that's indeed what we did. Of course, this just makes our work easier. It's not an RCE that will give us the payout, but it makes it really easy for us to not only get access to the device's memory, reverse engineer it, and perform our research on it, but also test both the dynamic testing and our POCs with the debugger attached, making the exploit development process a breeze in comparison to what it would be without it. That's actually scary, and don't look at it only from an attacker's or even a researcher's perspective. Let's look at it from a manufacturer's perspective. Let's look at it, and yes, from this perspective, and do you think that actually they don't care at all about their intellectual property? And even if most of the code base it's not yours, as we will see for this target later, you don't care about the parts you actually developed and make your product actually yours. I can literally dump, copy, obfuscate, and develop the same product without even trying to copy it. This actually tells you a lot about these companies and what they're trying to achieve. But this is a topic for another talk. After we open the firmware, we immediately get to see that it's unencrypted. Due to the ARM architecture, we also have a lot of tools to decompile the code with not so many errors. But something that stands out immediately is all the references to Tuya. While the name might not ring a bell to most of you, I'm pretty sure that at some point you actually interacted with a Tuya device, and it's one of the biggest platforms that the manufacturers use to develop IoT devices. As a big part of the code is available and open source, this helps us move easily to instrumentation fuzzing and code review for parts that were not properly decompiled, and also to avoid all the mapping and cleaning of the firmware in this case. And while this is not as easy as it looks, we can start taking into account what are all the interfaces, analyzing the attack surface that we have in hand, and isolating the functionality of the unit. With Wi-Fi, Bluetooth, and NFC, of course, the possibilities are endless, and the points to look are a lot. After some time over the binaries obtained by the target previously, and the code itself, there was a familiar reference in the documentation of Tuya, which is basically a highly integrated wireless chip implementing the Wi-Fi stack of the device. The interesting thing is that it's the entry point for several IoT devices, as it runs a full-fledged firmware, and there is even a common jailbreak method, which allows users to block the cloud connectivity of the target device, or devices in general. Of course, this gave us high hopes, but first of all, it's out of scope for this talk, as we need to talk more about hardware, but also because the device was not vulnerable to this jailbreak. The keen eye of some might already show that there was a binary supplied to the exploit POC, though. And this actually was not the binary of the main ARM MCU that we dumped previously, but the binary of the Wi-Fi chip itself. Going through the datasheet of the chip itself, and by using the BK7231 tools or whatever, we were able not only to access one of the two UART interfaces that the package has, but to dump the firmware itself and analyze any potential modifications and proprietary changes that can help us exploit zero-day vulnerabilities in this case. No proprietary communication, no encryption, no obfuscation. Everything unlocked and served to us for review. And apparently, all these were known. Considering that we already grabbed the full firmware and were able to tamper with the device, we didn't care about Wolfbox locking the interface for future updates. So we moved forward with responsibly disclosing the vulnerability, and the answer, of course, was that the vulnerabilities are known and that they are not willing to fix them. Seems like a trend in this world, right? After that, we went through with our research with the target of attending Pwn2Own Automotive during January in Japan, last January. After some time, and after getting ready for the competition, GDI posted this on their blog, outlining a brief analysis of the target and sharing the information of the unlocked SWD interface. While it was giving a head start to researchers, there was less than a month to the competition, so not a lot there. We applied for the specific category we were interested in over email, though we did not receive an answer from the committee whatsoever. While we didn't give up, it was not so clear till last minute if we will be able to join the competition, and the worst part was that we didn't even know why. 5 days before the competition, we received this, and in the end, our mail for some reason ended up in the spam folder, and of course, with no clarification, no plans were made, no trip to Japan, and no Pwn2Own for us. What we get out of this story? The fact that commercial devices that have actual physical protections like NFC user access control and app lock have unlocked and easily accessible hardware debug interfaces. Accessing the device for only a couple of minutes will potentially allow malicious actors not only to access the debug interface easily, but to completely tamper with this device, as there is no write protection on the MCU implemented, gaining persistence and remote access as the device is connected to the internet and potentially accessing sensitive functionality, as there is an external physical layer connecting the charger with the vehicle that is charging over power line communication and the vehicle-to-grid protocol. And in contrary to similar tampering stories from phones and other IoT devices, this is a device that is built to be set up and used outdoors, in garages with weekend security outside of houses for overnight charging, and in places that malicious actors can easily access without getting noticed. And of course, there is more to the story. The device is, of course, vulnerable to a lot of things, as it was proved in Pwn2Own and internally. And the interesting part is that if we take into account that a similar firmware runs in tens of millions of devices, vulnerabilities affecting this charger can affect from your smart thermostat to your smart Roomba and all. But these are part of a different talk, so let's keep focusing on the hardware side of the things and see some more practical examples of vulnerabilities we commonly see in the wild and the conflict they create both between teams and also between what is real and what is just an excuse. Now, most of you might say that this guy came here to show us an unlock debug interface and go. And you would be right. So let's not just stop to the easy targets. Let's see another manufacturer from my personal research stack of these devices that actually went one step forward and protected the available debug interfaces on the target board. Not only that, but there were no headers and mostly no obvious traces that we could map to something. So of course, this was the moment to reverse engineer our target hardware. We fired up the microscope and started gathering information from all around the board, getting us deeper and deeper into the rabbit hole. Now it's worth mentioning that this device is an ECU, or electronic control unit, from inside the vehicle. And it implements a specialized automotive-specific architecture, which architectures like this, mainly Tricore and Renesas, are used by safety-critical components due to their real-time responsiveness nature and additional functionality we will see later that targets these components specifically and their intended functionality. So now an interesting thing about these components is that many times they don't come with only one controller, but two, or even in many cases more than that, to accommodate for safety-critical errors. Basically, this happens because an instruction needs to be executed twice in either of the two different controllers. In this case, the secure and application controller, or two different isolated cores, and then compared between the two. If the output of the instruction is the same, it gets executed. If not, a fallback procedure has to be followed, depending on the system. Of course, this architecture is applicable to higher severity related devices like airplanes with more secure controllers needed, but this is out of scope, at least for today. Why this is important? Because in the devices where this is applicable, their failure will result in loss or damage of equipment, environmental harm, injury, or even death of the user and surrounding people in some cases. And moving closer to the hardware, we see that once again, not only the supplier was kind enough to spoil the fun and tell us when one of the JTAG headers is on the board, but they included a second part of the board with traces for the secure controller. Unfortunately, this time, after connecting my debugger, I discovered that both debugging interfaces were actually locked. But after I desperately started clicking on my power supply, I realized that something really interesting is happening. Here you see the user interface of the Tricore debugger connecting to the interface that we discovered, and you can see that the device is actually locked. Down you can see the power supply and the debugger connected to the ECU, where, as I said, I started clicking the power supply. Of course, I had some input to know that this is an actual vulnerability, and you can see that we actually got debug access in the start of the boot process. So yes, we got access to the secure controller. In this case, we basically got to enable the debug access in a really short period of time during boot. As a result, we can control the execution and dump the memory of the vulnerable controller. And this is not the only case where we managed to exploit a target because of small thresholds that can be utilized to trick the ECU into giving us access, and the enumeration of services and accesses in different timeframes of the boot sequences can be heavily beneficial in this case, as they can lead to access to different parts of the memory, either completely allowing access to the debug functionality, or just the part of the memory which is accessible at the moment. For example, access to the bootloader firmware while the target is initializing the boot sequence. Of course, in our example, we can see an exaggerated example of this attack, where we had around 1 second to perform the attack, but in more advanced microcontrollers, it worth implementing an iterative approach of what we saw to evaluate situations that allow similar functionality in way more strict timeframes with sole purpose to hide the fact that allow this in the first place. I love this meme because it depicts exactly what we go through in this industry. And not only this industry, because there is a really well-known phone SoC manufacturer which actually allows a similar bypass with a lower threshold in their developed SoCs. I actually tried to talk with them. They answered that this is up to spec, so I'm ethical enough to not make fun of them at this point and this talk, but how many SoC manufacturers do you know and are out there? Now that most of you are a bit less skeptical, let's go through another cool one in this Jaguar ECU. And because we are talking about a telematics unit, there is a Qualcomm modem SoC running, which comes with these magical pins that, if sorted, provide us a nice Qualcomm download mode. And after discovering some other pins seemingly matching a USB port pinout and performing the dangerous act of connecting a random USB from an ECU purchased from eBay, we realized that our assumptions are correct. After that, once more, we managed to dump the firmware and discover several vulnerabilities in both microcontrollers, including weak sources of randomness, weak cryptography, and other aspects that allowed us to compromise the unit completely from the application layer protocols, and in many ways, even remotely, as these protocols many times get exposed through the internet. For the context, this is the complete compromise that was discovered in this ECU with the POC that I presented in DEF CON last year. The point I want to make here is not the POC itself, but the fact that to exploit both the vulnerabilities, a hardware component was needed. Additionally, we can see that one opening and the bad design decision on the hardware security of the device allows for extensive research by malicious users with vulnerabilities that not only apply to one unit, but to potentially millions of devices. I urge you to watch my talk from last year's DEF CON, where I unveiled the exploit like this, the exploit, affecting millions of devices in the wild, while the OEM tried to undermine it by accusing me that I collaborate with hostile nations. So from last year, I keep extending my research, and at the point of this talk, I have responsibly disclosed 24 vulnerabilities outside of my commercial assessments of critical and high severity, leading to complete compromise of the target ECU in most of the cases. Out of them, 4 were approved and CVs were assigned, and 20 were completely neglected. Basically, the manufacturer didn't care to answer and handle it despite my extensive effort to contact the applicable people. But something worth mentioning, especially in this talk, is that a big portion of those vulnerabilities were discovered in the first place because of hardware issues and misconfigurations like or similar to ones that we talked previously. As I said in the start of the talk, I'm leading this amazing team at Auxilium, where I have successfully completed more than 200 penetration testing and research projects. This means that I got to work with a variety of people: engineers, management, hardware and software designers, architects, you name it. This not only gave me a holistic view of the industry, but it exposed me to discussions that let me understand how big corporations operate, what their strong points, and more importantly, what are their weak points. In the context of a project, though, what is really interesting in the last 5 years is the introduction of regulations around the globe, like the R155 for United Nations, the JASPAR for Japan, and others, and the enforcement of security assessments for vehicles and automotive components before the production, as well as maintenance of this security posture. Mainly because of that, as no one would do something that is not forced to do, that's why I have a job, and most probably that's why we keep having a job, automotive manufacturers started building cybersecurity goals, architecture, and design vehicles, and perform the threat analysis with that in mind. This can be good, but can also introduce several pitfalls. And during one of our assessments, where we discovered one of these vulnerabilities, reported it, and started the discussion about severity, scores, and applicability, the OEM's feedback was that this finding will not be fixed as it's out of scope. An easily accessible debug interface proven that can be bypassed either by normal methods or side channel attacks is out of scope. And I had to ask, what's the answer? Basically, it is required to exist by the cybersecurity requirements and threat assessment in order to allow easy access during a forensics investigation. And of course, it requires not only physical access, but to pry open the device and analyze the target hardware, which, as we already showed, in most cases, it's trivial. But nothing new here. That's how our whole industry works, and that's Thanks to all the people that raised the significance of these issues during the 2 days of Off by One, including the 2 amazing keynotes from yesterday and today that I really enjoyed. Now, regardless of what manufacturers say and use as excuses, there must be secure alternatives. And of course, that's what we should answer here in order for this talk to be successful. Regardless of the fun we had by all the different compromises, we need to be able to discuss, supply some constructive criticism, and strive for a safer future regardless of the stubbornness of this industry. While the situation we described earlier is the reality we face daily, debug interfaces can and should be protected, and it can be achieved with several methods and strategies. Surely we can implement software protections from the most obvious one being passwords and the more advanced one being public infrastructure implementations with securely stored certificates. Of course, these come with their own flaws. You will be surprised if I tell you how many times I saw password reuse, not only from one device to another, which should never be done, but even from one service to another. A more logical and practical way that makes it extremely expensive for an attacker to approach it is, of course, hardware mitigations. From scraping completely any traces, headers, and signs of those interfaces to completely fusing the availability of those on the SoC itself. Of course, dedicated attackers most of the times will find a way and will go through everything that is served for them. But in the end, it's not about how exotic your new fancy protection from space is, but about how you design those protections and to be unreasonably expensive for attackers to approach at the first place. It's different when you easily expose a VCC pin of the chip with no internal capacitors to compensate for voltage changes, which will lead to an easy voltage glitch target, and completely different story when the attacker needs $200,000 just to start analyzing the chip and performing laser and like exotic side channel attacks. And of course, stripping out everything from a hardware perspective means that we should have alternatives for forensics investigations or any other reason these logs might be needed. And these alternatives exist. We are building digital security for the last 40 years or more. Don't tell me that no one thought about those issues till now. To start with, we have to mention that considering we are working with automotive components, there are several automotive-specific interfaces and buses that handle communication between different ECUs and external devices. These range from old and outdated CAN buses to single-pair Ethernet implementations built specifically for the automotive and FlexRay for high-bandwidth automotive communication. With all these, not only low-level secure implementations can be developed, but a wide variety of higher-level protocols and methods are supported for secure and safe communication between ECUs and external devices that may or may not need needed for data extraction. Undeniably, if you see my past talks, you can clearly see my love for CAN and UDS. The CAN bus is a vehicle bus that manages the communication between the different ECUs in a vehicle, and FD for flexible data rate is an extension to this protocol that allows for high bandwidth and high performance connections. On top of that, and on the CAN communication itself, developers can and have implemented several security features like encryption with AES or message authentication with SecOC, and automotive-specific implementation for message authentication. In addition, several application layer protocols exist, like UDS and XCP, which can be used and implemented securely by using services like 27 for security access or 29 for certificate security access. If implemented correctly, this can provide an adequate challenge response or certificate-based user access control, which can distinguish users and allow access to specific parts of memory, which will provide crash logs, system crash dumps, and other valuable for forensics data only to users that are authenticated for this specific reason. Here we see a real-life example where we are reading data from specific data identifiers or memory locations under the UDS service read data by identifier. This can be done directly from the available interface of the device. It can store a reasonable amount of data, and if required, it can be protected under security mechanisms like the ones we mentioned previously. In similar fashion, services that can read memory directly from the device also exist, which can allow reading only from specific regions of memory and only for specific users. Now, of course, this is only the one solution, and it is unfortunately mentioned because while CAN is an archaic interface, iterated to death at this point to be sustainable with modern hardware, it's archaic and we should slowly move on from it. And I say this because better alternatives exist with the same amount of copper needed in the vehicle, which can support the same application layer protocols as CAN, but with all the additional protections and research that has been done in the last 60 years. This is Automotive Ethernet, a 2-pair Ethernet implementation, which of course supports robust security protocols like MACsec and TLS, but also supports everything that was discussed previously, as well as heavily developed and assessed methods for data exchange. This would be an ideal scenario where forensics investigators would be required to obtain a certificate from manufacturers which will allow them to access specific memory regions or specific logs served over a service in the Ethernet interface of the target ECU. There are, of course, reasons behind the use of CAN, but let's first start by applying this to all the ECUs that already implement Automotive Ethernet and move on from there. Of course, even if we use secure implementations for these externally available interfaces, we have to do so in a secure way and maintain trust and integrity of the whole system. Internal hardware protections should still be maintained or implemented, like hardware security modules, in order to have secure key management, secure and properly random cryptographic operations, and secure storage for sensitive data. On top of that, secure boot should also be implemented to ensure that no tampering took place during or before the crash, and ensure that only authorized software is running on the ECU at all times. On top of that, some other challenges that need to be resolved is properly secure data extraction during forensics, is that robust authentication protocols. Of course, when we talked about UDS and challenge response mechanism, yes, it might be secure, but only as secure as its implementation. Lightweight protocols, integration with hardware security modules and secure key storage, effective authorization mechanisms to prevent misuse, and secure session management and auditing of access attempts. Of course, there is also the elephant in the room, remote access, which I can see how it is already implemented and how it can be implemented in my industry. And to be honest, I'm not really confident, mainly due to data retention and privacy concerns. But we have to cover it as it's a potentially viable solution, which if implemented, it has to be done through anonymized data that, of course, are already shared in many cases with the secure backend connection of modern vehicles, and with real-time data sharing utilizing the eCall or telematics ECUs for sharing of data before, during, and after the crash. Of course, if the ECU is not severely damaged. And there is one more solution, implementing a dedicated physical interface, only accessing the specific information, probably isolated in the physical level, or handling through a secure external processor. It will be a specialized and standardized port for this exact use, obscured and difficult to access, of course, and completely isolated from any other debug functionality. Imagine it like the airplane's black box. Basically, during a crash, we don't need access to the whole code base of the airplane, but only the data that can be potentially related to this specific crash. With the automotive components, the big difference is that after a forensics evaluation, most probably the components will end up in a scrapyard, where people like me or malicious actors will go search for these components. Of course, this will increase hardware complexity, this solution, in order to be implemented properly, so I don't see it happening, at least for the near future. I guess at this point we need to summarize a bit and highlight that there is no one solution to rule them all. It needs to be a multi-layered, per-case security approach, which is designed from the ground up with security in mind. So I would say that manufacturers need to prioritize communication protocols and go away from hardware debug interfaces that can provide additional unintended functionality to malicious users. Integrate secure hardware and software solutions like hardware security modules, secure boot, and OTA updates when feasible, and develop dedicated secure storage partitions only for forensics data. Of course, enforce strong authentication, user access controls, and authorization, and collaborate in the industry to start building secure industry standards for everyone to use. Everyone will end up benefiting from those, protecting intellectual property, preventing unauthorized and unintended access, enable reliable post-accident investigations, and contributing to a safer future. And here we come to the serious finale. My rhetorical question is always if they even care. And if you ask me seriously, I honestly don't know. I met a lot of people from different backgrounds and cultures, people that actually care and people that wanted to show they care. And while looking at systems like the PlayStation, running non-safety critical chips that implement state-of-the-art mitigations for these issues, and our computer on wheels cannot even mitigate the basics, I'm left to wonder, is there any light in the end of the tunnel? And my answer is that it's up to us, all of us here, to make the best out of it, the best out of our work and our research, to pass on the culture to people that we're working with from higher to lower level, not with bitching, not with attitude, but with scientific proof, with our POCs, with our posts and our talks. And yeah, let's make the world a safer place for everyone, one POC at a time. Thank you.
We will now open the Q&A to the floor. If anyone has any question.
You can also find me in the lunch. I know that everyone is hungry now. So.
If not, I've received a question. So have you ever encountered a situation where you can't find the pin information online or cannot identify what it does? In that sort of situation, how do you extract the firmware? What's your approach and methodology on it?
Yeah, I think there were a lot of, like a couple of talks that they also discussed this topic that, you know, they might have like scrapped surfaces on the chip, or like they remove the serial numbers so they avoid, you know, like backlogging or searching for the data sheets. In these cases, you can always like desolder and remove flash memories. If that is not possible, you can mainly like search for online sources to find out if there are any references to the chip used. So usually there will be solutions because there is not so many chips around there. Like you can always backtrack and find some information. Thank you.
Nice.
Thank you all.
All right. Thank you, Thomas, for the great presentation.